So now we get to exercise number 3. We are going to do for BatchNorm this magic. Now we get to exercise, and we are going to do for batch normalization exactly what we did for cross-entropy loss in exercise number 2. That is, we are going to consider it as a glued single mathematical expression and backpropagate through it in a very efficient manner, because we are going to derive a much simpler formula for the backward pass of batch normalization. And we're going to do that using pen and paper. So previously, we've broken up batch normalization into all of the little intermediate pieces and all the atomic operations inside it, and then we backpropagated through it one by one. Now we just have a single sort of forward pass of a BatchNorm, and it's all glued together, and we see that we get the exact same result as before. Now for the backward pass, we'd like to also implement a single formula basically for backpropagating through this entire operation, that is the batch normalization. So in the forward pass previously, we took H pre-BN, the hidden states of the pre-batch normalization, and created H pre-act, which is the hidden states just before the activation. In the batch normalization paper, H pre-BN is X and H pre-act is Y. So in the backward pass, what we'd like to do now is we have DH pre-act and we'd like to produce DH pre-BN. And we'd like to do that in a very efficient manner. So that's the name of the game. Calculate DH pre-BN given DH pre-act. And for the purposes of this exercise, we're going to ignore gamma and beta and their derivatives because they take on a very simple form in a very similar way to what we did up above. So a bit like I did before, I started off the implementation here on pen and paper, and I took 2 sheets of paper to derive the mathematical formulas for the backward pass. And basically, to set up the problem, just write out the mu sigma square variance, xi hat and yi, exactly as in the paper, except for the Bessel correction. And then in the backward pass, we have the derivative of the loss with respect to all the elements of y. And remember that y is a vector. There's multiple numbers here. So we have all of the derivatives with respect to all the y's. And then there's a gamma and a beta, and this is kind of like the compute graph. The gamma and the beta, there's the x hat, and then the mu and the sigma squared, and the x. So we have dl by dyi, and we want dl by dxi for all the i's in these vectors. So this is the compute graph, and you have to be careful because I'm trying to note here that these are vectors. There's many nodes here inside x hat and y, but mu and sigma square are just individual scalars, single numbers. So you have to be careful with that. You have to imagine an example. I would suggest that you go in the following order: 1, 2, 3, 4 in terms of the backpropagation. So backpropagate into x hat, then into sigma square, sort, and on a piece of paper. If you want dl of dxi hat, then we just take dl by dyi and multiply it by gamma, because of this expression here, where any individual yi is just gamma times xi hat plus beta. So didn't help you too much there, but this gives you basically the derivational graph, and derive what is dl by d sigma square. And then what is dl? So give it a go, and we have to remember again, like I mentioned, that there are many x hats here. And remember that sigma square for dl by d sigma square, we have to actually consider all the possible paths that we basically have that there's many x hats, and they all they all depend on sigma square. So sigma square has a large fan out. There's lots of arrows coming out from sigma square into all the x hats. And then there's a backpropagating signal from each x hat into sigma square. And that's why we actually need to sum over all those i's from I equal to 1 to m of the dl by dxi hat, which is the global gradient, times the xi hat by d sigma square, which is the local gradient of this operation here. And then mathematically, I'm just working it out here, and I'm simplifying, and you get a certain expression. For dl by d sigma square. And we're going to be using this expression when we backpropagate into mu and then eventually into x. So now let's continue our backpropagation into mu. So what is dl by d mu? Now again, be careful that mu influences x hat, and x hat is actually lots of values. So for example, if our mini batch size is 32, as it is in our example that we were working on, then this is 32 numbers and 32 arrows going back to mu. And then mu going to sigma square is just a single arrow because sigma square is a scalar. So in total, there are 33 arrows emanating from mu, and then all of them have gradients coming into mu, and they all need to be summed up. And so that's why when we look at the expression for dl by d mu, I am summing up over all the gradients of dl by dxi hat times dxi hat by d mu. So that's this arrow, and that's 32 arrows here. And then plus the one arrow from here, which is dl by d sigma square times d sigma square by d mu. So now we have to work out that expression, and let me just reveal the rest of it. Simplifying here is not complicated, the first term, and you just get an expression here. For the second term, though, there's something really interesting that happens. When we look at d sigma square by d mu, and we simplify, at one point, if we assume that in a special case where mu is actually the average of xi's, as it is in this case, then if we plug that in, then actually the gradient vanishes and becomes exactly 0. And that makes the entire second term cancel. And so these, if you just have a mathematical expression like this and you look at d sigma squared by d mu, you would get some mathematical formula for how mu impacts sigma square. But if it is the special case that mu is actually equal to the average, as it is in the case of batch normalization, that gradient will actually vanish and become 0. So the whole term cancels, and we just get a fairly straightforward expression here for dl by d mu. Okay, and now we get to the craziest part, which is deriving dl by dxi, which is ultimately what we're after. Now, let's count, first of all, how many numbers are there inside x? As I mentioned, there are 32 numbers. There are 32 little xi's. And let's count the number of arrows emanating from each xi. There's an arrow going to mu, an arrow going to sigma square, and then there's an arrow going to x hat. But this arrow here, let's scrutinize that a little bit. Each xi hat is just a function of xi and all the other scalars. So xi hat only depends on xi and none of the other x's. And so therefore, there are actually, in this single arrow, there are 32 arrows, but those 32 arrows are going exactly parallel. They don't interfere, they're just going parallel. Those 32 arrows, or there are actually, in this single arrow, there are 32 arrows, but those 32 arrows are going exactly parallel. They don't interfere, they're just going parallel between x and x hat. You can look at it that way. And so how many arrows are emanating from each xi? There are 3 arrows, mu, sigma squared, and the associated x hat. And so in backpropagation, we now need to apply the chain rule, and we need to add up those 3 contributions. So here's what that looks like if I just write that out. We have, we're chaining through mu, sigma square, and through x hat. And those 3 terms are just here. Now, we already have 3 of these. We have dl by dxi hat, we have dl by d mu, which we derived here, and we have dl by d sigma square, which we derived here. But we need 3 other terms here. This one, and this one. So I invite you to try to derive them. It's not that complicated. You're just looking at these expressions here and differentiating with respect to xi. So give it a shot, but here's the result. Or at least what I got. Yeah, I'm just differentiating with respect to xi for all of these expressions. And honestly, I don't think there's anything too tricky here. It's basic calculus. Now what gets a little bit more tricky is we are now going to plug everything together. So all of these terms multiplied with all of these terms and added up according to this formula. And that gets a little bit hairy. So what ends up happening is you get a large expression. And the thing to be very careful with here, of course, is we are working with a dl by dxi for a specific I here. But when we are plugging in some of these terms, like say this term here, dl by d sigma squared, you see how dl by d sigma squared, I end up with an expression, and I'm iterating over little i's here. But I can't use I as the variable when I plug in here, because this is a different I from this I. This I here is just a placeholder, like a local variable for a for loop in here. So here, when I plug that in, you notice that I rename the I to it. And so you have to be careful with that. When you're plugging in the expressions from here to here, you may have to rename i's into j's, and you have to be very careful what is actually an I with respect to dl by d xi. So some of these are j's, some of these are i's, and then we simplified this expression. And I guess like the big thing to notice here is a bunch of terms just gonna come out to the front, and you can refactor them. There's a sigma squared plus epsilon raised to the power of -3/2. This sigma squared plus epsilon can be actually separated out into 3 terms. Each of them are sigma squared plus epsilon to the -1/2. So the 3 of them multiplied is equal to this. And then those 3 terms can go different places because of the multiplication. So one of them actually comes out to the front and will end up here outside. One of them joins up with this term, and one of them joins up with this other term. And then when you simplify the expression, you'll notice that some of these terms that are coming out are just the xi hats. So you can simplify just by rewriting that. And what we end up with at the end is a fairly simple mathematical expression over here that I cannot simplify further. But basically, you'll notice that it only uses the stuff we have, and it derives the thing we need. So we have dl by dy for all the i's, and those are used plenty of times here. And also, in addition, what we're using is these xi hats and xj hats, and they just come from the forward pass. And otherwise, this is a simple expression, and it gives us dl by dxi for all the i's. And that's ultimately what we're interested in. So that's the end of BatchNorm backward pass analytically. Let's now implement this final result. Okay, so I implemented the expression into a single line of code here, and
only thing is I'm not paying that much attention to how it is getting calculated and how I can calculate that, because I don't think that much level of I don't think that much level of expertise I need, so that's why but anyway, I will try to practice this again if I can build it and do it, but that's the reason I'm just seeing what he's doing and not trying to calculate on my own like I was doing before. And gain into bn sorry.
And you can see that the max diff is tiny, so this is the correct implementation of.
much understanding of the piece of code that has been here, and somehow I don't believe we need to go that internal again. Is something we should be knowing, but somehow I don't think as of now we need this level of information. Anyway, we'll again go through all the videos once again to all of this, but yeah,
this formula. Now I'll just basically tell you that getting this formula here from this mathematical expression was not trivial, and there's a lot going on packed into this one formula. And this is a whole exercise by itself, because you have to consider the fact that this formula here is just for a single neuron and a batch of 32 examples. But what I'm doing here is we actually have 64 neurons, and so this expression has to in parallel evaluate the BatchNorm backward pass for all of those 64 neurons in parallel and independently. So this has to happen basically in every single column of the inputs here. And in addition to that, you see how there are a bunch of sums here, and we need to make sure that when I do those sums, that they broadcast correctly onto everything else that's here. And so getting this expression is just like highly non-trivial, and I invite you to basically look through it and step through it, and it's a whole exercise to make sure that this checks out. But once all the shapes agree, and once you convince yourself that it's correct, you can also verify that PyTorch gets the exact same answer as well. And so that gives you a lot of peace of mind that this mathematical formula is correctly implemented here and broadcasted correctly and replicated in parallel for all of the 64 neurons inside this BatchNorm layer. Okay, and finally,
okay, I think I found this BN raw react BN raw finally.
all of the 64 neurons inside this BatchNorm layer. Okay, and finally, exercise number 4 asks you to put it all together. And here we have a redefinition of the entire problem. So you see that we reinitialize the neural net from scratch and everything. And then here, instead of calling loss.backward, we want to have the manual backpropagation here as we derived it up above. So go up, copy paste all the chunks of code that we've already derived, put them here and derive your own gradients, and then optimize this neural net, basically using your own gradients all the way to the calibration of the BatchNorm and the evaluation of the loss. And I was able to achieve quite a good loss, basically the same loss you would achieve before. And that shouldn't be surprising because all we've done is we've...
Okay, I'm getting... So we've completed this size 4. logits is here. The logit max is here. The logit max is here. The logits. The logits are here, and after this, right, HW2B2. I think this we calculated is from dbn raw. We calculated this. So till here we'll go off. So till dbn bias we need to dbn bias. Okay. This indentation issue is that thing. So dbn bias we calculated. After that, right, so we are calculating directly this individual here, right? DHP react, it is here. DHP react is here, and DHP react. So I think we have all of them. So we have clubbed nearly these many lines into one. Oh, one more thing we did right initially. This is correct is what I am trying to. Anyway, and after that, sorry. Sorry. Okay, we are calculating all the losses here. So DC is calculated DW. I'm just checking from here. DW1 is getting calculated, DB1 is calculated, W2B2, W2B2, DBN gain, DBN bias, BN gain, BN bias. Okay, he's taking care of this itself, that in 100 it will work, so let's see where it went. Unplug this. it's running fine. It will take some time to train. I'm not sure from where this part of code is coming. Why again they are getting calculated? Oh, okay. So what he's saying is, sorry, where the code went. So what he's saying, when we were training, right, we were training based on the small batches that we are pushing, right? Something like yeah, for 32 examples. So all the mean and everything that were getting calculated as part of it, right? For batch normalization was, you can say, mean batch, mean variance of the batch, mean of the batch. Now he's saying when we are trying to do inference and everything, right? Why we need to do that? We should use global mean and global variance. So that's what is written here. So you are getting the embedding for the whole training data. So it is checking all the training data. So all linear operation, everything we are going into, and these two variables is calculated. The batch norm, mean and variance for whole of the front. This is what we'll use while inferencing. Okay, got it. Where it went. Yeah, this explanation, right? After this, why we need this batch normalization? It will run, okay, and then we are trying to check the loss. Training loss, but the same thing we are using. Calculating HP react twice as a we're doing a Tanh of that. So whatever we are getting output, right, we are normalizing it here using the BatchNorm mean, and we are feeding it into the Tanh layer. Whatever output we are generating, right, we are doing a softmax to get the probability, and then we are trying to predict from the probabilities. We are picking up one element it is trying to predict, and we are adding that to the context vector. Okay, so what all the probabilities that we got, right, so we fed in the so this is pretty interesting. So interestingly, we are putting the 0th element, no, sorry, so all are zeros. Okay, I think 0 means the first word in the vocabulary, so we can check that part. Yeah, the 0 is dot, so that's what we are starting with. So it's like initially all of them are like dots. Okay, uh, and we feed that into the neural network, and it makes prediction for one of the words. Okay, and we add that to that, so it will be dot 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 dot, and then you will get that one word that came here, and the output we are appending it. Whatever that index, say it gave me um, 4, it gave me. Okay, so I'm putting in 4. Okay, so it is like 0 0 0 0 0 then 4, that means dot 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 and then D. Okay, so D is the one that the prediction came out of the model. Next time again we take the same context, that 0 0 0 0 0 4, we feed into this. Okay, again it makes a prediction, say it makes a prediction of 7, so 0 0 0 0 4 and then 7, that is D and G, and again so it will go on and on and on. way it will keep going on and on and on and on, because it's a while true, right? If again we receive a dot, unless that it will do that. So we get a word in that way, like this, something like, say we get Olivia, that gets printed, and that will run for 20 more times, so we will get 20 words one after the other. It is 20,000 and we are in 2 lakhs, so it will take some time. You will see the loss is also going down. So I will pause the video. Once we have the results right, we will see what we are getting. Okay. So finally the training is done. The minimum error that we could get is 1.88. And then these are the words that we are predicting: Yuma, Elisa, Yanum, Zaklo, Rayla, Mora. At least feels like name or gives a sense of name, but again, yeah, I mean, every country, every region has a different culture of way of giving names. So someone coming from India seems like, okay, means Yuma still where, Halisha still, I mean, at least okay, means at least sounds like name, or like that, not something random or jumbled words.
Code that we've already derived, put them here and derive your own gradients, and then optimize this neural net, basically using your own gradients all the way to the calibration of the BatchNorm and the evaluation of the loss. And I was able to achieve quite a good loss, basically the same loss you would achieve before. And that shouldn't be surprising, because all we've done is we've really got into loss.
Where is that loss calculation? Okay, I missed the spot here. .07, yeah, near about similar.
Backward, and we've pulled out all the code and inserted it here. But those gradients are identical, and everything is identical, and the results are identical. It's just that we have full visibility on exactly what goes on under the hood of loss.backward in this specific case. Okay?
Oh, sorry, I don't think you are able to hear that, right? Sorry, really sorry.
Okay, read, and then here as we derived it up above. So derive your own gradients, and then optimize this neural net evaluation of the loss. And I was able to achieve quite a good loss, basically the same loss you would achieve before. And that shouldn't be surprising, because all we've done is we've really got into loss.backward, and we've pulled out all the code and inserted it here. But those gradients are identical, and everything is identical, and the results are identical. It's just that we have full visibility on exactly what goes on under the hood of loss.backward in this specific case. Okay, and this is all of our code. This is the full backward pass, using basically the simplified backward pass for the cross-entropy loss and the batch normalization. So backpropagating through cross-entropy, the second layer, the 10H nonlinearity, the batch normalization, through the first layer, and through the embedding. And so you see that this is only maybe, 20 lines of code or something like that, and that's what gives us gradients. And now we can potentially erase loss.backward. So the way I have the code set up is you should be able to run this entire cell once you fill this in, and this will run for only 100 iterations and then break. And it breaks because it gives you an opportunity to check your gradients against PyTorch. So here, our gradients we see are not exactly equal. They are
I think it should be P and this grads is something I am calculating. Okay, and piece that's getting and for compare, right, it used to be mine by this, so mine is m grads by this. Billion.
are approximately equal, and the differences are tiny, 1 in -9 or so, and I don't exactly know where they're coming from, to be honest. So once we have some confidence that the gradients are basically correct, we can take out the gradient checking. We can disable this breaking statement, and then we can basically disable loss.backward. We don't need it anymore. Feels amazing to say that. And then here, when we are doing the update, we're not going to use p.grad. This is the old way of PyTorch. We don't have that anymore because we're not doing backward. We are going to use this update where you see that I'm iterating over, I've arranged the grads.
Okay, I got it.
To be in the same order as the parameters, and I'm
Hopefully this doesn't change much.
zipping them up, the gradients and the parameters, into p and grad, and then here I'm going to step with just the grad that we derived manually. So the last piece is that none of this now requires gradients from PyTorch. And so one thing you can do here is you can do with torch.nograd and offset this whole code block. And really what you're saying is you're telling PyTorch that, hey, I'm not going to call backward on any of this. And this allows PyTorch to be a bit more efficient with all of it. And then we should be able to just run this, and it's running. And you see that loss.backward is commented out, and we're optimizing. So we're going to leave this run, and hopefully we get a good result. Okay, so I allowed the neural net to finish optimization. Then here I calibrate the BatchNorm parameters.
So this is with the third one, I think DB1. I think this is what happened. Okay, it's running. So it's supposed to be just 200, so we are expecting just an array of 200 rather than 1 cross 200. Okay, it will again take some time.
This run, and hopefully we get a good result. Okay, so I allowed the neural net to finish optimization. Then here I calibrate the BatchNorm parameters because I did not keep track of the running mean and variance in the training loop. Then here I ran the loss, and you see that we actually obtained a pretty good loss, very similar to what we've achieved before. And then here I'm sampling from the model, and we see some of the name-like gibberish that we're sort of used to. So basically the model worked and samples pretty decent results compared to what we were used to. So everything is the same, but of course the big deal is that we did not use loss.backward. We did not use PyTorch AutoGrad, and we estimated our gradients ourselves by hand. And so hopefully you're looking at this, the backward pass of this neural net, and you're thinking to yourself, actually that's not too complicated. Each one of these layers is like 3 lines of code or something like that. And most of it is fairly straightforward, potentially with the notable exception of the batch normalization backward pass. Otherwise, it's pretty good. Okay, and that's everything I wanted to cover for this lecture. So hopefully you found this interesting, and what I liked about it, honestly, is that it gave us a very nice diversity of layers to backpropagate through, and I think it gives a pretty nice and comprehensive sense of how these backward passes are implemented and how they work, and you'd be able to derive them yourself, but of course in practice you probably don't want to, and you want to use the PyTorch AutoGrad. But hopefully you have some intuition about how gradients flow backwards through the neural net, starting at the loss, and how they flow through all the variables and all the intermediate results. And if you understood a good chunk of it, and if you have a sense of that, then you can count yourself as one of these buff dojis on the left instead of the dojis on the right here. Now, in the next lecture, we're actually going to go to recurrent neural nets, LSTMs, and all the other variants of RNNs. And we're going to start to complexify the architecture and start to achieve better log likelihoods. And so I'm really looking forward to that, and I'll see you then.
Okay, let this thing run. Okay, we are getting a huge error which was not supposed to be, so we need to stop this block. Okay, finally it's stopped. Let's enable this code. So it should be running, yeah. And then we calculate if the gradients are coming out fine or not. Oy, sorry. Oh, sorry. Wait a minute. This was supposed to be, and we tell it to not calculate the grad. Okay, wait a minute. So this whole thing again we need to enable this as a commented out. Yeah, this thing is required, else how we'll calculate that. So it ran. That's where the issue is. It's taking log probes. Let's anything here from oh mm. This needs to be calculated, right? But they are not calculating it. I'm not sure why they are taking directly the logits means the logits, so they are directly here. What happens to all of this? I think they have merged it, is it? Oh, okay, so whole of this, right, they are calculating using softmax. We have broken down this layer into this, right, and log probs is true. D probs is also true. Put it under one. So this is true. are doing directly the cross entropy. They are not calculating one by one, one by one, one by one. That's the reason we are getting like this. Because whatever we are using this, right, this is the initial one that has been called. So we are using this log props to calculate. So they have merged all of this into single. Means we can do that as well if I believe so. So here, right, after logits we can do this. See, so here it is same as f dot cross entropy. What we can do is so here okay, this is what it is. Now it works. So what we can do is we are not going to use this loss.backward. We'll update using our own explanation. Okay, and it is not required. Let's see if the error reduces. At least we are calculating the gradients perfectly. We'll just wait for the next error to come less, then we can pause it and see. So we could see that the errors are reducing using the backpropagation that we defined. That's pretty good, huh? Nice. Okay, we'll wait once the results are out, right? Then we'll go through it. So finally the training is done. So this is the loss that we are getting on training and validation set. Morakaya, still a bit name like Kitila Narvan. I don't know if people have such names or not, but Kaya is still Madhela might be. I'm not sure, but anyway, we were. So this was all with our back propagation that we wrote, and we got the answer to it. So finally, let's see. Next we'll go through the LSTM and the scenes and the other architecture. So